All right, yeah, welcome back. As we continue this course, the next thing we want to do today is to test ANOVA for our analysis. Don't forget, we claim by machine learning that the two diseases we try to we predicted using different machine learning language algorithms. They are different. Okay, each of them, they are different. So we have to support this with a test, a morphometry. There must be a test to support it. And you could remember that ANOVA is analysis of variance means is to compare the means of two or more independent groups in order to determine whether there is statistical evidence that the associated population means are significantly different. And then we have proved that these are different, significantly different by even by our SVM scatter plot shows that they are not the same, they are different. All right. Also, our accuracy show that they were able to we were able to predict them with high accuracy, means they are different. So we must be able to support this with statistics test, which is ANOVA. We are going to use ANOVA to do that, and this is other parametric test actually. So but assumption must be met. At least we must meet at least 3 assumptions. The first assumption is normality. That is, the sample data come from a population that approximately follows a normal distribution. And we're going to test that. The second one is homogeneity of variance. The sample data come from a population with the same variance or with equal variance. Okay, so equality of variance. So also we're going to test, we don't need independence test because we have agreed that the sample data consists of independent observations. Okay, they are independent observations actually. So we don't need to bother about that. But we need to also check for outliers. The sample data don't contain any extreme outliers. So this first, second, and fourth we'll be looking to see that this data is free from this meets these assumptions. Then we can go ahead to use parametric tests, which is ANOVA. But if it does not meet, then we can switch over to non-parametric test, which is a Kruskal-Wallis. Kruskal-Wallis is a counterpart of ANOVA. So we can use either two of them, depend on the assumption that you're able to meet in this. So let's go to our data first and see what I'm talking about. So our data is here, all right. Our data is, so we are going to let's move this one from here. Let's move it here to the front here before we go further. Let's move it. Let's insert. All right, let's move it here so that then delete this one. We can move to the front. So we can copy select all, copy. Want to move this one to let's go to paths now. Open paths. So because we don't have any identity or subject identity in the for a row by row section, so we use we use column attributes. We don't have a row by row attribute. So we just click we click for column attribute only. So we only have headings, PC1, PC2 like that. So we click on this A. This is very important. So if you miss this, then you have to be doing it again and again and again. So we now paste here. You have copy already, paste here. Then the next thing you open here under this spot, you select group. So this is a group variable, all right. Then you off this. So automatically provide a numeric identity by itself. So now the first thing we want to check is to check the normality of this. So we don't need all of them. We don't need all the PCA. Okay. So we need only one. This particular group variable and one one predictor is enough. Okay, one variable is enough. Okay, so let's first check the let's check the summary and normative test of this each of them and see which one that you can use. So one is okay. So anyone that is meets the assumptions we can use. So we click here, see summary test under univariate, and don't forget there are three things you must understand, or four, in this under this testing. Number one is that the skewness must as close to zero as possible, must be as close to zero as possible. All right, don't mind the negative, and kurtosis also must as close to zero as possible. That's number one. Number two, that the Shapiro test must not be significant. All right, it must not be significant, so it must be greater than 0.05. That's what it means. Okay, so this must be clear. And also for homogeneous variance, the Levin test must not be significant as well. Okay, must be greater than 0.05. So if this one is met, then you can go ahead and use ANOVA for this experiment. But if not, you can switch over to Kruskal-Wallis, and Wallis you can use to test your analysis. So let's see. Here we have assumption. I mean, we have a summary here, and this skewness is not too close to 0.4. It's not too close to 0, and kurtosis is not so close to 0. So this one. Let's also check again the normality test here for the same. Shapiro test is a 0.025, which is more than, which is unicant already. So we cannot use this particular variable, because this variable is not significant. It's not meeting the normality test. All right, so we have to let go of this. So let's check the second one. Statistic of second one. Okay, this one is okay. This one is a skewness 0.02, which is as close to 0 as possible, and kurtosis also 0.09, which is also as close to 0 as possible. And then this one is very close to normality. So don't mind the negative sign there showing the direction of the data. All right, so we can use this, but let's first confirm by using the normality test. Let's confirm. All right, so Shapiro test P is not significant. You can see 0.9. Which means it meets the assumption. All right, so we can go ahead and use a second variable to test our ANOVA. So we don't need to bother about Kruskal-Wallis anymore. So now you just select this line, all right, together. This line together. That's all you need. You select this line and this line together. By holding your control key, you can select the two separate together. So we need to perform our ANOVA on this. We just need to check the p-value and possibly degree of freedom. So now you come here, click here, go to ANOVA, then several sample test. Okay, you click here. We didn't meet the assumption. We click on Kruskal-Wallis. All right, that's what we use. But because assumption is met, then we can use one with ANOVA to test our experiment, our two diseases, whether they are significant or not, whether they are different or not. So using the mean, now you can see here that this 0.026 is significant, and for permutation also significant for permutation also. So this means that the means of the two equal groups are significant. It means that they are different. All right. So even Levin test here for homogeneous variance is also it's not significant, which means it meets the assumption of a Levin test. All right, homogeneous variance. And even when you look at F test, also it's okay for unequal variance. So you can see here that now we copy this. We do F and P. That should be enough for us. Okay, F and P. All right. So you got F equals to 5.03, while P equals to 0.026. So or 0.027. That is our P value. So this one will be kept. You can copy this out. You can just write it down and put it in your thesis. All right. So that is what you use, which means that we have concluded that this particular two diseases are different. So because they are significant. So that is that for now. So we'll continue from there next time. So you can take note of that. Thank you.